Hi everyone, my name is Mihai Donțu. I work at Bitdefender and I lead the Linux development team that's in charge with developing a VMI API for KVM. And this is a progress report for a presentation that I held in 2017 where we laid out an initial plan for VMI. It was very alpha code, not a lot of features in it. This is a report for the 2 years that have passed since then. And it's connected to the presentation that Jun Nakajima and my colleague Andrei Luțaș had yesterday about VBH and HVI. This part of this API plugs into that HVI technology to have it work on top of KVM. This is my agenda. It's pretty packed. I haven't really timed it well, so I hope I'll be able to go through it. I'll just compress some slides into one big phrase. First, I'll begin. Why is Bitdefender pursuing VMI? Well, it all started a couple of years ago when we got a pretty loud confirmation that certain entities with serious financial backing were collecting exploits, critical exploits. We call them 0 days. They were not disclosing them to the public, and they were using them for their own purposes. These exploits managed to subvert all in-guest security boundaries and be able to persist, exfiltrate data, and so on. The majority of the cases, the source of these exploits begins with the software itself. The problem is that the kernel is very complex. Those people who work on the Linux kernel or even or just KVM have a pretty good image of how complex Linux is these days. The Windows kernel is just as complex, and on top of that, a couple of years ago it grew a Linux in it. Browsers are fantastically complicated pieces of software. And bugs that appear in in either the kernel or various software, in many cases manage to achieve privilege escalation and take full control of the operating system. There are various processes, various methods to harden these components. However, it takes a little bit of time, and we're looking through VMI to take a few steps forward until everyone agrees on how to properly fix things. So what exactly is VMI? Well, it's the ability to look from outside the operating system and identify it, to determine whether it's a Windows OS, whether it's a Linux OS, and identify the software that is running inside it, right? Various applications, browsers, Office, readers, all that, and also determine if there is potentially harmful software running inside of it. Achieve all this without the use of any guest tools. Anything, you don't need software running inside the guest OS to tell you, okay, that process has started, that process is opening those files or doing God knows what. The advantages of a security solution based on VMI is that it can achieve better isolation. Right? The hardware itself basically changes personality whenever it enters the guest, and it provides a pretty solid boundary between whatever the guest is running, the guest itself, and the security application. It also removes the reliance on the operating system for it to function. It does not need the cooperation of the operating system. Most of the time, a security application using VMI will completely stop the operating system and inspect whatever is going on. Potentially, every now and then, ask it to page in some information. And it also minimizes the interference with the operating system. You don't need drivers. You don't need to do any tricks inside of it that in future versions of that operating system might prove to be a bad idea and crash it or whatnot. The typical cases for using VMI are detecting memory violations. Okay, so using EPT, we set some hooks, right? Mark certain areas either read-write or read-execute or unwritable and so on. And violations that can begin with buffer overflows, right? Somebody starts writing way beyond the normal boundaries and breaches the stack page guard and triggers an event that then a security application can start looking to see what's going on. It can be used to prevent code injection. It's very easy to determine which process inside the guest OS is writing where and whether it's allowed to do so or not. It can guarantee integrity of in-guest security. So a security-based or a VMI-based security application cannot, for example, do file inspection. That will penalize the performance way too much. So what it can do is make sure that a dedicated security application running inside the guest remains untouched by a potential attacker. It can also make sure that the drivers and the kernel itself is not compromised. There's no patching, there's no tricks, there's no driver objects being overridden somehow or anything. And it can also keep a close eye on every process being spawned inside that operating system. So how is Bitdefender using VMI? Well, through HVI, and which employs EPT in the case of Intel CPUs, it essentially secures the OS kernel. That's pretty basic. There are many solutions out there that achieve the same thing. It does this by enforcing code, right? It remains read execute, data remains read write, stack, read write, heap, read only, so on. It protects core pieces of the operating system, right? The interrupt descriptor table, the global descriptor table, the system services, and so on. The system CR3, credentials, and all that. It secures the driver objects, makes sure that pointers inside every driver object, which in case of Windows, are registered and by the driver, and the pointers are inside the driver itself. So it makes sure that remains the same. It enforces certain harder features. For example, supervisory mode execution prevention is not turned off by some malicious application or driver. It makes sure that the kernel system call entry point remains the same. x86 has a number of MSRs who indicate where the CPU should start executing every time a syscall is made. And the protection can be extended for user mode applications as well. This is a little bit more complicated because applications have their own page tables, have their own memory allocation built on top of the operating system memory allocation algorithms. But it can be doable. By closely monitoring the OS kernel, it can then infer what users' applications are started and provide the same security for code, data, prevent code injections, prevent DLLs from being, or shared objects, not necessarily Windows specific, even though the majority of the use cases I'm talking here are pretty well connected to Windows. Making sure system services are not overridden. They are not hooked in any way. And it can also terminate applications. So for example, if an application is determined to have an abnormal behavior or outright malicious, it can also be terminated. So the architecture that we're envisioning with HVI looks pretty much in this fashion, whereas the KVM hypervisor is running a number of virtual machines, but one of these virtual machines has the sole purpose to monitor all the others, right? This is a special virtual machine. It's measured booted. It's separated from the network. It has in a separate class than all the others. All right, so for our KVM work, the patch series that we're working on is still in RFC. We've reached the 6th version. We started in 2017, and pretty recently we've published the last one. In these 2 years, we've had a number of difficulties. For example, controlling the extended page tables. We tried to mimic the behavior on Xen, which is our first implementation of HBI, by simply hooking the page fault handler. That didn't really work very well because there are many places in KVM where the EPT is slightly adjusted. We also had to work around emulator limitations. The x86 emulator in KVM supports as many instructions as there were needed at the time KVM was developed. With VMI, almost the entire set is required. In support for the entire x86 instruction set is required. However, there's a workaround for it, which is single stepping. It's a pretty straightforward mechanism. Use VMX's monitor trap flag for the vCPU that caused the page fault, but we wanted to move forward without removing the EPT permission bits. We simply single step the current vCPU while all the others are suspended. And then after single stepping, we restore permissions in EPT and let the guest go do its thing. Another issue we're still working on it is the inter-guest page sharing, or remote mapping, as we call it. We're working, I think, on a 50 version, the fourth one being published in August. Whatever we did, we simply could not manage to get KSM kernel same page merging and the transparent huge pages to cooperate. So currently, KVMI requires these two features to be disabled. Another difficult task was since the security virtual appliance, the agent of the security application communicates with the host through a BSD socket, getting code inside the kernel to do basic networking tasks without avoiding deadlocking or doing operations in interrupt context, illegal operations in interrupt context. We also tested a number of versions of this algorithm and eventually decided that while a kernel worker receives control commands, so to speak, from the security solution, it creates queues for every vCPU. The problem being that at the time, most of the time, whatever the security application requires from the host requires that the current pCPU has the VMCS context loaded. And there's a sensitive locking mechanism there that you can either do it from a separate thread than the QEMU thread, or you either create a queue for every vCPU. And another complicated task was exception injection. We use this to inject page faults, for example, inside a guest. For example, when we need to look at a certain piece of code, however it's being paged out, we inject a page fault and tell the guest operating system to page it in. We have hooks on the guest page tables, and we see when the operating system populates the required entry. Exception injection is pretty tricky to get right. We eventually settled for where we leave KVM to do all its work, all its internal bookkeeping, queue exceptions, queue interrupts. And at the end, right before we enter the guest, if we want to inject an exception, we'll look at how the vCPU has been configured, and if there's something pending, we tell the security application, no, try again later. And that got it to work. So regarding controlling the EPT permissions, as I said, there are various parts in the KVM which do their own adjustments to EPT depending on what they need. We decided to use some feature from Intel, which is page tracking. Intel uses it for virtualized GPUs. And we extended it with 4 callbacks, right? Pre-read, pre-write, pre-exit, create slot. The first 3 are for validation, right? Before an actual operation happens inside the guest, we validate it and have the ability to veto it. Create slot is simply for allowing us to keep a consistent view of the permission the security application has set every time QEMU moves slots around. Regarding the emulator, most of the faults occur when the guest does simple page table walking. Right? The guest page tables are hooked, and the hardware every now and then will need to adjust the access and dirty bits in the page tables. Those events, those EPT violations, write violations, are of no interest for a security application. So what we do, we use another piece of code from KVM to simply emulate the page walk. Regarding the memory mapping, we're following some advice from, I believe, if I'm pronouncing his name correctly, Jérôme Glizet. And it's still in alpha stage. I hope we'll be able to publish something by the end of the year and manage to get KSM working with it, KSM and THP working with it. Cover this. Something else that we're working on and have not yet published is support for VMFUNC, alternate EPT views in particular, and virtualized exceptions. This allows us to limit the number of VM exits from the guest while introspecting it. Another feature is sub-page protection or sub-page permissions, which allow us to monitor areas of data that are not paged, are not aligned to the page size, right? Are smaller, 16 bytes or whatever, but live with code that gets frequently modified. Most of the KVMI work right now happens in-house. We're hoping that in early 2020 we'll move everything out and have all the development in public. A few words on AMD support. Currently, it's not possible to do introspection the way we want it. That is real-time introspection, mostly because the NPT is a normal page table. It has no support for execute only, for example, which we require sometimes to trick certain parts of the Windows kernel. And mostly, if one hooks the guest page tables, every walk of the guest page table becomes a right violation, which slows everything down terribly. There's also no equivalent for VMX's monitor trap flag. Maybe something can be concocted out of the native debugging features, but we didn't get to study it well. If anyone from AMD has advices on how to overcome these, they're more than appreciated. There's also QEMU words and modifications on the QEMU side. They've been published on GitHub. We haven't yet submitted official patches to the QEMU mailing list. Mostly hooks that will tell your security solution when to disengage, right? When the VM is migrated, rebooted, suspended, something like that. The way we tested, every combination of operating system out there, we're talking close to 100-something virtual machines, and unit tests for every attack technique supported by the HVI technology. And we do end-to-end tests, which covers 100% or very close to it. Every KVMI code path is being exercised in this manner. I have a few slides on performance numbers. I don't know if I still have time. So there's a comparison with Xen. Xen uses what I would call lightweight event channels. That is, there's a ring buffer shared by the hypervisor and the guest doing the virtual machine in which the security application is running. This ring buffer is accessible from user space. It simply reads entries from there and then notifies the hypervisor when the vCPU can continue operation. And then there's KVM, which for introspection we use virt.io. On top of it, we use vhost-vsock, which is derived from VMware's vSock. And on top of it, BSD sockets layer, everything running in user space. So it's quite a detour taken until messages sent from the security application to the kernel, to the host, get there. With that in mind, the performance of the KVMI compared to the Xen version, which is what we consider to be the mature one, is very close. And this is what we find today in mainline. There are some vhost-vsock optimizations from Red Hat that bring the numbers almost identical or very close to the Xen ones, which is weird. Again, the communication channel with the Xen hypervisor is very, very lightweight, and the KVM one has a number of layers, and yet somehow the Linux kernel manages to win at this. These are these are some numbers with a set of Windows virtual machines, and simply testing every browser in how long it takes it to open a number of links, 20, 30, something like that. And these are for various Linuxes. Actually, it's Ubuntu 18.04 running Unix bench. Again, the numbers, even without the vhost-vsock patches, the numbers are pretty close to Xen. So HVI running on top of KVM using KVMI. Among all the attacks that it can prevent, these are the most popular ones. I guess everybody recognizes at least two of these. And I have to give a shout out to Mathieu Terral for working on implementing the libVMI driver for KVM on top of KVMI, and a number of really nice projects he's working on. And with this, I'm severely out of time.
Questions? So not directly related to KVM, but do you have any trouble identifying those attacks that you can mitigate versus so-called benign behavior that is exposed by typical DRM software?
Well, DRM software might look malicious.
Definitely, yes. Like they use a lot of techniques that you would expect from malware. Yeah.
Exactly. Unfortunately, there's a lot of software out there that does really dubious things. And specifically for that, we have an exception mechanism. That is, we first let it fail terribly, then we look at what it tried to do and create a sort of, I wouldn't say a signature, because the AV industry has exploited that to death. A fingerprint, if you will, that will determine, okay, this is DRM, just leave it do its thing. And it's accurate enough not to let actual malware get away.
Okay, thank you.
Okay.